Kok perlu.
Hello. Hi.
Good morning, Prof. Ming-Che Hu. Can you hear me?
Yes.
Yeah,
Hi. Yes, I can hear you.
Yeah.
So is my microphone okay?
Yes, it's okay.
Okay. Can I try my PowerPoints? Can I try
Yes,
my
please.
slides?
Please go ahead. Please go ahead, Prof.
Okay. Yes.
Aku tak tinggal.
We can see your slide presentation, Prof.
Yes. So does is my PowerPoint working okay?
Yeah, it is
I'm
working.
moving downward. Okay.
Okay.
Right. Thank you very much.
Yeah, thank you, Prof. Ming-Che Hu.
Yes.
We will be starting shortly.
Okay, sure.
Mbak Pratiwi sudah siap?
Sudah, Pak.
Ya, baik. Benar ya. Okay, thank you very much. Welcome to Prof. Ming-Che Hu. We are very pleased to have you join our webinar today. And we look forward to your presentation and valuable insight on spectrum optimization analysis in water resource management. Thank you for taking the time to share your knowledge and expertise with us. Without further ado, let's get started with today's webinar, and we are very excited
Recording
to hear
in progress.
Prof. Ming-Che Hu presentation and hope this discussion will provide valuable insight for all of us. Now, I would like to invite Ms. Pratiwi, our MC, to take it from here and officially start the webinar.
Okay.
Please go ahead, Ms. Pratiwi.
Yeah, Bismillahirrahmanirrahim. Good morning, everyone. Morning. Assalamualaikum warahmatullahi wabarakatuh, and the greeting to all participants joining us today. Welcome to International Guest Lecture Batch 7 2025, hosted by Department of Mathematics, Universitas 11 Maret. So happy to see you all of here, guys, both our lecturers, students, and of course our distinguished guys from Taiwan, Professor Ming-Che Hu. Is that correct how I say your name? Today we'll be diving into a really
correct.
interesting topic. It's about spectrum network optimization for water and energy system management. It's gonna be exciting, insightful, and
UNS.
a little bit hopefully inspiring for all of us. Before we start, I just want to introduce myself. My name is Pratiwi Dianingsi. You can call me Pratiwi or TV for short, and I'll be your master of ceremony in this session. Let's have a great time together, everyone. Okay, before we jump in, here's the flow of our session today. First is opening, second, the welcoming speech, the third is lecture session, and also Q&A, and also close by closing. All right, let's get started. To open this event officially, let's welcome Professor Siswanto, the head of our Department Mathematics Universitas 11 Maret, to give the welcoming remark. For Professor Siswanto, the time is yours.
Thank you, Pratiwi, for taking the time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning and greetings to all. We are grateful to God Almighty for this opportunity given to us all. Honorable Professor Ming-Che Hu, our keynote speaker from Department of Bioenvironmental System Engineering National Taiwan University. Dear colleagues, students, and all participants, it is with great pleasure that we from the Department of Mathematics at Universitas 11 Maret welcome you to this International Guest Lecture 7 edition. Today, we will learn about spectrum network optimization for water and energy system management. This topic is very important in today's world of science and technology. We are very thankful to Professor Ming-Che Hu for sharing his knowledge with us. We hope that the ideas shared today will give us new insight and inspire us in both our research and teaching. We also appreciate everyone who is joining us today. We hope this event will help strengthen connection between universities, expand our networks, and give us a better understanding of how research can help solve real-world problems. Let's make the most of this opportunity to learn, discuss, and work together for the advancement of knowledge and progress. Thank you very much, and I wish everyone a successful event. Assalamualaikum warahmatullahi wabarakatuh. When I return is to the MC.
Microphone. Sorry, you forgot to turn on your microphone.
Oh, Pratiwi.
Okay, sorry. For Professor Siswanto, thank you for the welcoming speech. And next, I want to introduce you for our speaker. Our speaker today is distinguished professor from Department of Bioenvironmental System Engineering, National Taiwan University, and he completed his PhD at the Johns Hopkins University, USA. It's very cool, and his bachelor and master degree at the National Taiwan University. His research focused on the water resource, energy system, and also environmental optimization, with the numerous international publications and several academic awards, including the Springer Nature Edition and Outer Surface Award 2025. It's a truly honor to welcome him today in this session, Professor Ming-Che Hu.
Yes.
No, yeah,
Thank you for introducing me. And
yeah.
okay, so let me share my screen. Hi, everyone. So you can all hear me. Okay. So you can hear me, right? And also my screen should be okay. All right. So first of all, I would like to thank the department chair to give an opening speech, and also I would like to thank the professor uh, could he for inviting me to join this wonderful events. And also thanks for the chairperson and also all those audience for this events. I'm very honored to be. I'm very honored to join these events. And yes, actually, in my lab, I also have some students from Indonesia. So I'm very happy to see to get to know all of you. So thank you very much for inviting me. And as I just mentioned, so I'm Ming-Che Hu, and I'm a faculty member from the Department of Bioenvironmental System Engineering. I'm from National Taiwan University. So I've been teaching for like about 18 years. And my research focus on the optimization and also some economic analysis and some data analysis, machine learning for the water resource system and also for some energy and nature resource management. So I know today I'm gonna give a talk to the student from the audience. Most of our audience are from Department of Mathematics. So I try to find some common interest between your department and my research. So basically, I apply all those optimization and all those data analysis model for the using all those system analysis for the resource management. So I'm more in between. So I know some system analysis model and also algorithm, but I'm also interested in how to apply those model and algorithm to analyze it for our environmental problems. So today I'm gonna introduce one of my research. Uh, so the model we developed is called the spectrum network optimization, and I'm gonna introduce some research how we apply this model for the water and the energy system management. So based on the name of this model, you can see that it's a network optimization. So if you ever take the linear programming course, you probably learn the optimization, you learn the network optimization. So basically this kind of optimization problem, they have the network structure. So you try to minimize all those uh, for example, you can minimize the total cost for the network optimization, or you can maximize the profit uh, for for the network optimization. But in our research, we need to combine the time series data with the network optimization. So we kind of include the Fourier transform with the network optimization together. So that's why we call our model spectrum network optimization. Later on, you will see more details. So before I introduce my methodology, I'm gonna give some background about my research problem. So everybody knows that climate change uh, have a serious impact for the our environment. So for example, for our water resource system, we have sometimes we have heavy rainfall, and sometimes we have we shortage. We have a water shortage. So we have more and more flooding, and we have more and more drought in later years. So you can see that, but this kind of climate change gonna have a huge impact for our water resource management. And on the right hand side, you can see that maybe some of you already know the TSMC. So TSMC is a very big chip making company from Taiwan, and lately they invest lots of money in the southern Taiwan. They built many factory to because the demand of the chips are increasing. So so TSMC they have more and more factory in southern Taiwan, and also on the other hand, the industrial water demand gonna increase because of those factory. So so the water resource management became a very serious problem in southern Taiwan. But on the other hand, sometimes the government, because the industrial water demand is important, because the industrial they can make lots of profit, and also the residential water demand are also important because we need water. Everybody needs water. So sometimes the government will suspend the all those agricultural water demand. They will suspend the irrigation to have to save some agricultural water resource, and then we can transfer the agricultural water resource to industrial or to the residential demand to meet all those demand. But it gonna become a very huge problem in agriculture. So farmers they lose their job, and then also lately people are talking about the SDG, and agriculture provide foods for the society. So agriculture is still very important. So our research is try to see are there any if there is any like a win-win situation, win-win strategy for the water resource management among all those sectors between industrial, between residential and agriculture. Are there any win-win strategy to do the water resource management? So this is our research problem. And so on the right hand side on this figure, so this is Taiwan, and the Taiwan is in the north of the Indonesia. It's in between Japan and the Philippines, and I guess the flight should be like 4 hours, 5 hours away from Indonesia to Taiwan. And you can see that there are some pipeline in this in the map of the Taiwan, because lately our government, uh, because in Taiwan we have many water resource system, and each water resource system we have the reservoir. In each water resource system we have reservoir to store water, and also we have river to provide the inflow water from the upstream to the reservoir. And also in each water resource system, we will build some pipeline to deliver water from the reservoir to all those to meet all those demand to the industrial, to the residential, and also to the agriculture. But lately, our government they try to build some pipeline between between systems. So we kind of try to connect systems together, and those strategy should be good because imagine that you have two systems. and system 1 have more water. System 1 have more water, but system 2 have water shortage. And then if you have a pipeline, you can deliver water from the system 1 to system 2, right? And if system 2 have enough water and system 1 doesn't have enough water, and then you can deliver from system 2 to system 1. If those two systems have enough water, and then the pipeline is, we are not gonna use those pipeline. And if those two systems have water shortage, and then we are not gonna use those pipeline to deliver water in between those two systems. So based on those four scenarios, you can see that the pipeline is always good if you connect those systems together, and then system can help each other. But the thing is that those pipelines sometimes you sometimes they are not very useful, because if those two systems they have the same pattern, their water supply have the same pattern. For example, if they're during summer, they always have lots of water for those two systems. So if their pattern are very similar, so when the system one have enough water and system two also have enough water, and then we are not gonna use the pipeline to deliver water between those systems. And if those two systems uh always have a water shortage together, and then we cannot use pipeline to deliver water as well. So if those patterns are very similar, sometimes those connections, those pipeline are not useful. So our research question is that how uh, which uh, which system, where are we gonna build our pipeline, and how can we make those pipeline are most useful, and also the size of the pipeline are also very important, because to build those pipeline can be, it's gonna need lots of budgets. So if you ignore the pipeline, and then the pipeline is always good, as I just mentioned, but to build those pipeline, you need lots of budget. So you need to consider the trade-off between budget and also the pipeline. Even the pipeline is useful for those systems. So we need some methodology. We need some model to quantify all those factors to measure the cost of the pipeline, and also the effect of the pipeline. And then we can see the trade-off between pipeline and the investment of the pipeline, and also the impact. If, for example, if the pipeline can lower the risk of the water supply, and then we can analyze the trade-off between the cost and the risk. Okay, because more cost might lower your risk, but if we don't have enough budget, and then we will lower our budget, but that will lead to more risk. So there are some trade-off between those factors. So we need a model to analyze this kind of problem. And if you look at the water resource system, so this is a water resource system in southern Taiwan, and each color represent one water resource system. So for example, this water resource system in Jiayi, and this orange one is in Tainan, and the red one and also green one are in Kaohsiung. They are all different water resources in southern Taiwan. And you can see some dashed line. Those dashed line are the pipeline between two systems. For example, you can see there is a pipeline between the red one with the green one. And the water comes from the upstream river. So those water are delivered from the upstream to the reservoir, and then we will deliver the water from the reservoir to meet all those demands, the industrial demand, residential demand, agricultural demand. And so we put all those demand in the bottom, and different color represent different water resource system. So we want to have one model to measure the impact the benefit of those pipelines. Okay, but as I just mentioned, all those inflow data, the what inflow water, all those data are time series data, and also the rainfall data are time series data, and groundwater are time series data, demand are time series data. So although this model looks like a network, right? So we deliver water from point to point and then to meet the demand, to meet the demand in the demand nodes. So this system looks like a network model, but we need to have optimization model. We try to minimize the water supply risk, and we need to consider the time series data in this network optimization. Okay, so so because we want to consider time series data, so we kind of incorporate the Fourier series with the network optimization. This figure just show you that the blue curve is the real data of the water supply, and the red curve is the Fourier decomposition of this inflow time series data. And you can see that when you add in more and more Fourier terms, and then the red curve will approximate the blue curve. Okay, so we will incorporate this idea with the network optimization. And so in this network optimization model, you need to consider the risk minimization problem, and also the constraint, the storage of the store to simulate the reservoir. We use ordinary differential equation to simulate the storage of the reservoir. So dSdt is the slope of the storage equals inflow function minus the demand function minus the water delivered from other network. Okay, so negative sign means that you deliver water from this system to other system, and the positive sign means that you have some water from other systems. Okay, so this ODE is a mass balance equation for each storage, for each reservoir, and also for the groundwater. If you learn something from the groundwater, actually, many people use the Laplace equation. So this is the Laplace equation. So this one is a partial differential equation, and this is the Laplace equation. So people are using the Laplace equation to simulate the groundwater, the mass balance for the groundwater. So in this model, you will have a risk minimization problem, and your concern will include some ordinary differential equation. And if you consider the groundwater, you will have a partial differential equation in your constraints. Okay, and before we get into the detail of our spectrum network optimization, I would like to give a brief introduction of the network optimization. So this is a traditional network optimization problem, and so this one is called the cost minimization problem. So you can see that. So first of all, you can see the directed network graph G, and this graph consists of finite sets of network capital N, and also the set of direct paths capital A, and those arcs showing the pairs of nodes in those nodes. And the Xij represents the amount of flow on each arc over time. And INI is the inflow of the nodes I, and the DEI is the demand of the nodes I, and the Cij is the unit cost for each arc. So you can see that, so because the Xij is the amount of the flow, and the Cij times Xij, summation of Cij times the Xij over Ij is the total cost of this network. So we try to, in this model, we try to minimize the total cost. And then later on, we will transform this model as a risk minimization problem. And in our constraint, so the network flow problem, the constraint of the network problem, they have a mass balance for each node. So the first term is the total inflow, total outflow. So Xij, summation of Xij over J. So this is the total outflow, and minus the total inflow. So Xki, summation of Xki over K. So this is the total inflow, and the equals the INI minus DEI. So this is the mass balance. If you move all those terms to the left, you will have a mass balance equal to 0. And then this mass balance equation should be sustained for each nodes. And also Xij is greater than or equal to 0 for each arc. Okay, so this traditional, the original network flow problem. But in this kind of problem, they didn't consider the Xij is a scalar variable. So, but in our water resource management problem, we need to consider the time series data. We need to consider functions. Okay, so for example, if we go back here, for example, this is one of the reservoir in this system, and in the original network optimization problem, you have inflow and outflow, and then inflow should be equal to outflow. So that's a mass balance equation for this network, for these nodes. But right now, the inflow is a function, is a time series data, and the outflow is also a time series data, also a function. So our model became a mass balance of functions. So we need to kind of transform this model. We need to incorporate the functions with this network optimization problem. So we were, so how are we gonna do this? So we will replace all those scalar. Instead of all those scalar, we will replace those scalar with the functions. So you can see that this is our new model. And if you compare this model with the previous one, you have Cij, Xij, and the Xij, and the Xki on the left-hand side. If you compare the original one with this one, you can see that the new model, Cij, Fij, and the summation of Fij minus summation of Fki. So everything are pretty much the same. The only difference is that I use the F to replace the X, because right now it's not a scalar, it became a function. So Fij is a function. It is a function. So right now our unknown variable became an unknown function in these variables. And also your cost is a function. And also your inflow, your right hand side, the inflow data and the demand data are both functions. So right now you have outflow function minus inflow function equal to the inflow function minus the outflow functions. Okay, so our mass balance constraint became the mass balance for the functions. Okay, for each nodes, your functions need to be mass balance. Okay, but if you go back to the water resource system, it's pretty intuitive because you have some inflow and also some demand, right, over time, and the the actual the actual water need to comes from other systems. Okay, if you uh have some inflow and also some demand, and if they are not balanced, those water should come from the upstream river or comes from other uh comes from other systems. Okay, and then eventually we need to mass balance over time. Every time we need to mass balance. If you didn't consider the storage, you we need to have the mass balance for each time periods, okay, and also for each nodes, okay. So if you compare this model with the previous, actually everything looks pretty much the same. The only difference is that we use the functions to replace the original scalars. Okay. So right now we have a functional network optimization problem. Okay. So we call it a functional network optimization problem. And you can see that it's a network, and then all those inflow, they are functions, and those water delivered from nodes 1 to nodes 2 are also functions. So the variable is f1, 2, and the water delivered from nodes 1 to nodes 3 is also functions. So it's the notation is f13, so it's also functions. So use the same notation, you will have this new functional network optimization problems. Okay. And also, we want to look at the dual variable of this functional network optimization problem. So we want to find the dual variable. Okay. So if you learn if you ever take the linear programming problem, linear programming course, you probably heard about the dual variable for the dual problem and also dual variable for the original problem. And of course, the network optimization problem also have the dual problem and the dual variables. But right now, our dual variable also became a functional dual variables. Okay, so for the network optimization problem, the dual variable are uh, for each nodes. So each nodes will have a dual variable. And right now, since we have a functional uh, network optimization problem, so right now our dual variable becomes a functional dual variables. Okay, so node 1 has a functional dual variables, and the functional 2 also node 2 also have a functional dual variable. This one also have functional dual variable. This one also have functional dual variables. And this we can also create we can also generate the dual problem as follows. So we will have dual variables, and in each variable, for each primal variables, we will have dual constraints for each primal variables. Okay, and this dual constraint will be gi minus gj less than equal to cij. Okay, so this one is a dual constraint for the primal variables, and right now this dual constraint also insists of the functions. So you have a function gi, and you have function gj, and you have a function cij. Okay, so right now it's also a functional constraint. Okay, and this our objective function for the dual problems. You can have this one, and uh, we need to notice that the dual constraint will become equality. So Gi minus Gj will equal to Cij when the primal variable is positive. Okay, so in the primal problem, if you have some water delivered from node 1 to node 2, and this variable will become positive, right? So it became a basic variables. And if this one become basic variables, and your dual constraint will become equality. Okay, so for example, in this in the original problem, if you deliver water from node 1 to node 2, node 2 to node 4, node 2 to node 3, so if you have uh, if you have this basic variable in f1 2, f2 3, and f2 4, and those basic variable will consist of spanning tree. And this spanning tree is also became a functional spanning tree. So for time 1, your spanning tree is like this. Time 2, uh, your spanning tree is like this. And maybe in some other time, your spanning tree will be different. Sometimes the spanning tree are the same for different time. And but sometimes your spanning tree are different. So your spanning tree will become a functional. So the spanning tree will change over time. Okay. So right now I write down the spanning tree, the capital G, as a function of t. So right now the spanning tree is a function of t. Okay. And those when you have a basic variable on this spanning tree, and then your constraint for those variables, for those basic variables, for this variable, for this variable, and for this variable, your constraint will become an equality constraint. So Gi minus Gj will equal to Cij. Gi minus Gj will equal to Cij. So the equality constraint will you will have equality constraint for this spanning tree, and also for this spanning tree, and for this spanning tree. Okay. And why this dual variable and also the dual problem became important? Because if when you work on the uh, network simplex methods, your your you also need some you also need your dual variables to simplify your calculation. Okay, so in here we introduce our primal problem, and also we introduce our functional dual problems. Okay, and since we let's take a close look of the mass balance equation. So you have the total outflow minus total inflow equals the external inflow. Okay, and you can actually decompose all those functions. You can also do perform the Fourier transform, Fourier series for each functions. So those functions can be decomposed into the Fourier series functions. Okay, so we write down the capital F here because we can do the Fourier transform for each functions. Okay, and then the generalized Fourier transform of the dual problem can also perform for these dual constraints.
Yeah.
So you can do the transform for the primal constraint. You can also perform the Fourier transform for the dual constraints. Okay. And right now we will move on to the network simplex methods. Network simplex method is a very basic method for the network optimization problem. But right now we want to expand this idea for our functional network optimization problem. Okay, so we want to establish construct a functional network simplest method for our new models. Okay, and for this model, first of all you need to compute your functional variables because this will provide you some information for you to introduce non-basic variables, the basic variables. Okay, and so first step you need to compute the dual variable, and second step you need to introduce a non-basic variable, and third step is you need to find the minimum ratio test to do the minimum ratio test and to find the variable to exist of the to leave the cases. Okay, so as we just mentioned, the spending issue became functional, and also those your dual variable also became functional. Okay, and then we can actually calculate the Vij minus Cij. So those are the cost for you to introduce the non-basic variables. Okay, but right now those variables also became functional. Okay, so Vij is a function of t, Cij also a function of t. So right now, for each time for different time you will have different functional variables. Okay, and then based on when you have the Vij minus Cij, you want to introduce the more positive Vij minus Cij to uh, you want to introduce a non-basic variable with the most positive Vij minus Cij to go into the basic variables. Okay, so right now this is a function and this is also a function, and the Vij is gonna equal to the dual variable minus the dual variable Wi minus Wj minus Cij. Okay, and so here is a dual variable and this one is also a dual variable. Okay, so we want to so right now it becomes functions, and right now we have the functions for the non-basic variables. Okay, and then we want to find the most positive one to introduce those non-basic variables into the these sets. And also we need to find the minimum ratio test. Okay, and when you do the network simplest methods, you just need to do a scalar. So you do the minimum ratio for all those scalar variables, and but right now it became functions. Okay, so when we introduce non-basic variables, we need to find the minimum ratio for all those functions. Okay, so for example, if you have two functions, you have this this uh, this curve one, okay, this break one, and you have the second curve, and this second curve is more thin. Okay, and if you compare those two curves, the minima of this curve is in here, the dash line. So it's in here. This is a minima. This is a minima. This is a minima. This is a minima, and this is also a minima. Okay, so you need to use this minima ratio test for those functions, and then you can by using this minima ratio test, you can see which non-basic variable is gonna leave the basis. Okay, so we kind of generalize our network simplest method, and right now we have a functional network simplest methods. Okay, so everything became functional. So your dual variable became functional, and when you introduce the non-basic variable with the most positive Vij minus Cij, it also became functional. Okay, so you introduce the non-basic variables, and also when you want to find the variable, the living basis, the variable for living basis, you also need to use the minimum ratio test to compare different functions to find the minimum minimum ratio for living basis. Okay, so we kind of generalize these network simplest methods. Okay, and also this functional network flow can also consider the storage. Okay, the original network optimization problem, they didn't consider time. They also, because they don't have time, so they couldn't consider storage. But right now, since our model, we replace the scalar variable with the functions. So right now we can consider storage. Okay, so if you compare this model with the previous functional network optimization problem, the mass balance should be equal to 0. But right now, we can consider the storage because in the water resource system, sometimes we have a reservoir, sometimes we have the dam, and they can store some waters. Okay, and so right now, if you consider storage, and our mass balance equation became the ds I dt equal to the total inflow minus total outflows. Okay, and if you assume the activity function are pretty much the same, and this the only difference is that the left hand side of the constraint. Right now we consider the storage for this water resource system, and if we want to apply the previous functional network simplest method for this problem, actually it's okay because for example, if you perform the Fourier decomposition for each for your constraint, originally you perform the Fourier transform for each right hand side, right? So inflow functions, demand functions, and also water from different systems. Everyone is a function, so you can decompose all those functions into the Fourier transform. But right now, the left-hand side is also a function because storage is a function, and the ds dt is the slope of the storage. This term is still a function. So of course we can decompose this function into the Fourier series. Okay, so right now we can decompose this mass balance equation into Fourier series. Okay, so we can perform the Fourier series for these constraints, and again we can perform the simplest method for these models, and also when you perform, there is something need to be noticed. So before you perform the Fourier decomposition for this mass balance equation, your mass balance is on the time domain. So every time you will have a mass balance, right? If you either have the mass balance for each time, or you store some water in the storage, and then the water will store over time. Okay, so but anyway, so the mass balance is sustained for on the time domain. But right now, if we perform the Fourier decomposition for each term, and then it's still, this equation is still equality constraint. But right now we will have the mass balance equation on the frequency domain, because we decompose all those functions into the sine function, cosine function with different frequency, right? If we use the Fourier, if we use the sine function and cosine functions, so we if we perform the Fourier decomposition, and then our mass balance equation will be the mass balance on the frequency domain. So what is the mass balance on the frequency domain? Actually, it's still very intuitive because all those sine function and the cosine function for the Fourier series, they are all orthogonal functions, right? So, for example, if you have some sine function on the right hand side, actually, if you have a sine function for the domain, actually you need to use the same function to supply water to meet this demand, right? You cannot use a different function to meet this demand because those functions are orthogonal to each other. So they cannot, for example, a cosine function from the if you have a cosine function for the inflow, the cosine function cannot be used to meet the demand for sine function for the demand. Okay, so the cosine function cannot cancel out the sine function because they are orthogonal to each other. So they cannot you cannot deliver the cosine function to meet the sine function. Okay, because all those Fourier functions are orthogonal to each other. So that's why we also need to have a mass balance on the frequency domain. Okay, so that's some intuitive for this if you perform the Fourier transform for the constraints. Okay. And so right now you have the network optimization problem, and each node has the storage. Okay, and you can perform the Fourier decomposition for those. You can generalize. You can also apply the generalized Fourier transform for these functions. You don't. You can use a cosine function, sine function, but you can also use some other orthogonal function to do the generalized Fourier transform. Okay, so those are the we also we have some those mathematical model, and we also try to have our we also write our Python code, our Python model to solve our problem. So, but to solve the real problem, we need to decompose our we need to discretize our model because continuous function is not easy to for the real because our real data are the discretized data. We have time series data, but we measure the data from time to time, and so the data is discretized. So we also write a Python coding to solve this discretized network, functional network optimization problems. So so the whole structure is that we incorporate the series with the network optimization, and the model will be look like this. And also we have the orthogonal functions for the we perform the network optimization. We perform the Fourier series for this network optimization problem because we need the orthogonal coordinates to find our optimization problems. Okay, so those are the Fourier decomposition. And this one is the discretized network optimization problem. So I'm not gonna go into the details, but let's take a close look of the equation number 2. So here you have the A in A I N minus A O U T. So this is the Fourier coefficient for the inflow minus the Fourier coefficient for the outflow, and also plus the Fourier coefficient from the network, and this will equal to the sum of the left hand side should be equal to 0 because this equation represents the mass balance on the frequency domain. Okay, because the Fourier coefficient should also be mass balance. Okay, for each frequency. Okay, so this what as I just mentioned, so this one is the mass balance for the frequency domain. Okay, so we decompose our functions to these Fourier functions, and then right now we have orthogonal coordinates, and then we can find the optimal solution for this network optimization, functional network optimization problems. Okay, so we create the Python model, and then so right now we also have some software. So if you have the functional network optimization problem, and then we can use this Python model to solve this problem, and we also develop this algorithm. So develop this functional network simplest methods for this problem. And those are just results from our problem. So we connect three systems together. So in southern Taiwan, we connect those three systems together, and then we try to deliver water to from system 1 to system 2, system 2 to system 3. And if you can compare the demand and supply for those systems, you can see that their patterns are pretty similar. Because right now we are optimize our we try to minimize the risk on the frequency domain, and this is on the frequency domain. So on the frequency domain, we ignore the higher, we ignore some Fourier turns. We only consider the first 10 turns. So because we ignore the following turns, so you can see that the patterns are very similar, but sometimes they have some very small, very high frequency noise difference. Okay. So those are the results from our systems. And okay, so that's the results from my network from my spectrum network optimization problems. And so right now, so in this research, we develop we establish this functional network optimization problem, and we also develop algorithm to solve this problem, and we also establish the Python model to solve the real problem, and okay, and also we also apply this problem to the energy system. I don't have the slides because I'm I run out of time, so I don't have the slides for the energy system here, but uh, think about the right now we try to find the optimal management of the water resource, right? So those water resources are different functions. So we kind of optimize those functions and then deliver those functions to meet the demand functions. So we kind of do it working on the management for the functions. And think about the if you consider the energy, if you can, for example, we also apply this model for the renewable energy investment problem. So uh, when people are working on the renewable energy, for example, the wind power, the solar power, the biggest problem is that those renewable energy, there are lots of uncertainty for the renewable energy production. So if you compare the renewable energy with the renewable electricity with those coal-fired electricity generation, the coal-fire or nuclear electricity generation, they are more stable. They can generate a very stable production. They provide a very stable production for the electricity. But the renewable energy, they have lots of uncertainty. So our problem is how can we uh, how can we combine all those uncertain functions, and then we want to have a stable we want to have a function more stable functions for the electricity to meet the electricity demand. So our renewable energy generation problem is also try to do the management for the uncertain functions. We try to combine all those uncertain functions and then create a more stable functions. So it's also a network optimization, and also those renewable energy, those electricity network is also a network problem. So we also try to minimize the risk for the electricity supply risk, and also we want to optimize. We want to management all those uncertain functions. So we have a network system, and we also have the time series data. We also have the functions because the renewable electricity generation are also functions. So we in our energy problem, we also need to combine the function with the network optimization problems. So that's how we apply this function spectrum network optimization for the energy management. Okay. So I also have some other research, but since I think it's almost time, so I will stop here and then I will take some questions. Thank you very much.
Okay, thank you very much for the insightful talk, Professor Hu. Now we'll open the floor for the question. If you have something to ask, feel free if you want to drop your question in the Zoom at the chat box. But I would like, I'm really happy if you want to raise hand and also ask your question by open your microphone and also your camera. But we wait for the question. I also have a question for you, Professor Hu. It's about the technical. I I mentioned
Yes.
in one PowerPoint in the dual condition where the GI minus GJ is equal to CEJ. You mentioned that it corresponded to FEJ greater than 0 in the primal problem. Could you please elaborate a little bit on how this relationship help us in interpret which arc are active in the network? Do you
Okay.
get my
Sure.
question?
Thank you. Yes. Yes. Thank you for your question. Let me share my screen one more time.
Yeah.
Here, right? We are talking about this, right?
Yeah.
Okay. So actually those ideas are from the network simplest methods. So and also I guess most of you knows the optimization. So in for the dual problem, if you want to generate your dual problem, you need to for every primal constraint you will have a dual variable, right? And also for each primal variable, you will have a dual constraint. So for this minimization problem, you will have you will have a maximization dual problems. Okay, and this constraint comes from here, comes from each primal variables. So each primal variables, so comes from each primal variables. And right now, since the primal variable is positive, is greater than equal to 0, so your dual variable in here is here. Your dual variable will be gi minus gj less than equal to cij. Okay, and since we have uh, in between the primal problem and the dual problem, we will have the KKT condition, because this one is linear programming problem. It's a linear optimization problem. So the KKT condition is necessary and sufficient condition for the optimal solution. So when your when your primal problem is positive, if it is positive, if your primal problem is positive, and then this one should be equal, the condition will become equality. And if your primal problem is equal to 0, and then your constraint will be like this. So this complementarity slackness condition for the KKT from the KKT. I'm not sure if I'm clear. So all those conditions are from the linear programming theory. So you have a primal problem, you have a dual problem, and then your primal your primal variable, and it should have the complementarity slackness with your dual constraints. So when this one is positive, so either one of them should be equal to 0. Okay, the complementarity slackness is either one of them should be should be equal to 0. So when this one is positive, this one should the gi minus gz minus cz should equal to 0. Okay, so this constraint will become the equality constraint. Okay, and then this is very important because for the for the for the network simplest methods, we can use the dual variable to calculate the cost for the non-basic variable. So in here, when you want to introduce your non-basic variables, uh, you you need to calculate the cost for each non-basic variable, and then we want to find the one with the most positive, right? And how to calculate the Zij minus Cij? Actually, we can use a dual variable to calculate. So that's the advantage for the network optimization. So once you have the dual variable for each nodes, and then for this network simplest methods, it's very easy to calculate the Zij minus Cij, and then it's easy for you to find the non-basic variable with the most positive variables. So you know which one is gonna be introduced into the basic variables. Okay, so that's why we need to calculate the dual variable. And then once we have this we have this equality constraint, we can use the spanning tree. So assume this assume this one is 0, and then you have this equality constraint. So you can based on this equality constraint, you can calculate the dual variable for node 2. And then because this one has the positive primal variable, so you can use this equality to calculate dual variable for this one. And then again, you will same logic, you can calculate the dual variable for this one. So finally, you will have a dual variable for 1, 2, 3, 4. Okay, so once you have a dual variable for 1, 2, 3, 4, and then you can calculate the those Zij minus Cij. So it's So you can find which variable you can introduce into the basic variables. So that's why we need the dual variables. And so this figure, if you go back and read the KKT condition in your linear programming, and then the difference between my research with the network optimization in the textbook is that right now it became function. So this one is function, this one is function, this one is function. But the original network optimization, those dual variables are scalars. Okay, but right now they are become functions. So that's the difference between my model with the original network synchronous methods. And but ideas are pretty much the same. So those equality and those final variable are positive. So those ideas are exactly the same with the KKT condition. Okay, so I hope I answer your question. Thank you.
Okay, thank you so much. And then I want to I want to read from the chat box. It's from Mahir. What potential limitation or assumption in the model, example in the pipeline capacity, could affect the accuracy or applicability of the purpose spectrum network flow optimization in real-world scenarios? How to answer that, Professor Hu?
I'm sorry because I tried to read the question, but I couldn't find the question, so I didn't focus on what you just said. Can you like quickly go over one more time with the question?
What the potential limitation?
I couldn't see the text.
Yeah.
Oh, limitation for my model. Okay, thank
Yeah.
you. Limitation for my model. I guess I'm not gonna share the slides one more time. So limitation. Let me see. Of course, because right now the model is network optimization problem, and also it includes the functions into this model. And the limitation is that, of course, you need a network problem, and then you can apply this model to that. If your problem is not a network problem, if your question your optimization problem is not doesn't have a time series data, you don't need to use my model for that one. So that's one limitation. And are there any other limitations? And also, okay, and also there are some, because I mentioned that we developed our algorithm for the functional network synthesis model, right? So we try to develop the functional network synthesis methods. We try to develop that one. And uh, when we introduce this, so there are three steps. You need to calculate dual variable, and then you find the non-basic variable to introduce into the basic variable, and also you need to find the basic variable to db the basis. There are three steps. So and the third step is based on the minimum ratio, and our concept are pretty much the same. But the difference is that our algorithm, when the db basis some the some basis, because right now it's a little different, because of the original simplest method, network simplest method, when you have one basic variable, and this basic variable leaving the basis, and then it totally leaving. But right now, because ours is functional, so maybe 80% of this function leaving the basis, and the other 20% are staying the basis. So the there are some difference between my model with the previous with the original network simplest methods, and that will create some difficulty to find the optimization model, because one because the original basic variable is gonna be a spanning tree, right? But right now the spanning tree became a functional, became a functional, became a functional. So one tree after one iteration of the simplest method, one tree might become two tree or three might become two tree, and the two tree will become more and more trees. So if we work on the continuous data, continuous function, because I mentioned that our network optimization model need to combine with the function or combine with the time series data. But for time series data, it's easy because if one tree became two tree became four tree, and then because the number of the tree are still limited. But if it's continuous, it will become more and more trees. So right now our Python coding are trying to work on the discretized data. Okay, so that's one limitation. Okay, I hope I am clear with your question.
Yeah, Mahir,
All right.
is that enough for you, or you want to ask more? Okay, see, he said enough.
Sorry.
Yeah. And then maybe one more question because we have a limited time. I want to pick one. It's from Catherine Monica. How might the future climate change scenario be incorporated into the spectral network optimization model to stimulate long-term impact on water resource connectivity and infrastructure investment priorities? How to answer that,
With
Mr.
what
Hu?
the yes I'm okay, sorry. Uh, I'm sorry. I missed the last part. I heard that her question is related to my model and also water resource. And but the question is, can you repeat the question?
How might the future climate change scenario be incorporated into the spectral network
Okay.
optimization? Yeah.
Okay. Yes. Because right now, our model can consider right now we can consider the we already incorporate the time series data with the network optimization. But for climate change, we this is a very good question. We consider this part because uh under the climate change, your water supply data might have different patterns, right? Because climate change has a huge impact for our environment. So the inflow data, outflow data, groundwater data might might be different. So we have been thinking about so those our model right now we transform from the time domain to frequency domain. The climate change, the pattern might change. So we have been to solve this problem. We have been thinking about incorporate the wavelet time series analysis with our network optimization. Right now, we combine the Fourier transform with the network optimization, but Fourier transform is a periodical function. So instead of Fourier transform, we have been thinking about the wavelet analysis, and wavelet analysis is also a time series analysis, but they can consider they can consider time domain and the frequency domain together. So which means that uh, you can still perform your frequency analysis, but over time, over a long time, under the climate change, your patterns might change. So you need to consider under the climate change, you need to consider time and the frequency together. Okay, so that's why we have been considered incorporate the wavelet analysis with the network optimization. And wavelet analysis is also a time series analysis. It's a little similar to the Fourier transform, so shouldn't be a problem to incorporate those models together. So this very good question, and we have been working on this ongoing research. So thank you very much for your question.
Big thanks to Professor Ming-Che Hu for joining us and sharing such a valuable insight today. And of course, to all the participant for being here and stay engaged. But Professor Hu, you need to do a closing statement. Maybe you want to give advice for us who really enjoy this session.
Yes, thank you very much for inviting me, and I'm very happy to be here. And as I just mentioned, I also have some students from Indonesia, and uh, we are also hopefully sometime maybe we can visit your hopefully I can find some chance to visit your university and in person to give a talk in person. So and if any of your faculty member or student want to come to Taiwan to do some research, welcome to contact me, and you can find my email, and later I can provide my email. So welcome to contact me on my presentation or any question about if you want to come to Taiwan to do some research. So thank you for having me, and special thanks for the Professor Kuti. So thank you for inviting me, and I'm very honored to have this chance to give a talk for your department. So thank you very much.
Yes, big thanks also to Professor Hu, and also thank you everyone. I want to close this session. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof. Hu. We look forward to future opportunities for collaboration. Yeah. Yeah, thank you very much, Prof. Hu.
Okay, so thank you very much. And also, thank you very much, Professor Kuti. So thank you very much. And
Yeah, thank you very much,
thank you,
Prof.
Chair. Yes, very nice to
Yeah,
meet you and your students.
yeah.
So
Thank you very much, Prof.
thank you.
Nice to meet you.
All right, so stay in touch. Okay.
Yeah,
All right.
okay.
And also, I can provide my slides and to
Oh, yes,
students
yes.
if
Thank you
it's
very
necessary.
much.
Okay. All right. Thank you. All right. So
Yeah,
see
see
all of
you.
you around. So thank you
Yeah,
very
see
much.
you.
Bye bye. Bye bye.
Bye bye. Bye bye, Prof.
Bye.
Bye bye.